Okay, so in the next part of this lecture, I want to discuss something new called Bayes' rule. This is a new technique that we haven't discussed thus far. It's very general, very useful for quantifying our uncertainty in model parameters. And I want to discuss it in the context of the linear regression problems that we've been discussing so far. So let's motivate Bayes' rule through ridge regression. So we've discussed the ridge regression objective function, where we saw that we were trying to minimize an objective of this form, where we sum the squared errors, and then this is a measure of basically of how well a particular value of the vector w can predict the data that we have. So by minimizing this, we're finding a w that performs very well on our data. And then this second term, lambda times the squared magnitude of w, in a sense is like a prior belief about what w should be. So in a sense it constrains w, it gives us, it imposes a prior belief on, in this case, the idea that the magnitudes of w shouldn't be too large. So this is a prior belief that we're using. And so the question is there a mathematical way to formalize this idea of imposing a prior belief on a model parameter or a model variable? And the answer is one answer is using the probability, the framework of probability and Bayes' rule, we can make some coherent, rigorous statements about what's going on. And so before I return to extending the ridge regression solution into a fully Bayesian realm, I want to quickly, very briefly, give a review of probability, what statements we make with probabilities, and also what we can do with probabilities. So the next two slides I think of as being mostly review, but I want to go through them to set the context for what we'll discuss later. So imagine that we have two events, A and B, that may or may not be related. So for example, A could be the event that it's raining outside, and B the event that the ground is wet. We can talk about probabilities of these events. So we can say that P of A, the probability of A, is the probability that it's raining outside, and the P of B, probability of B, is the probability that the ground is wet. We can also talk about conditional probabilities. So these are probabilities of events given knowledge of other events. So the probability of A given B, which is what this is saying, is the probability that it's raining given the fact that I know that it's wet. So the probability of A given B. And the reverse of that is the probability of B given A, where we're saying that the probability that the ground is wet given that it's raining outside. So these are conditional probabilities. Finally, we can talk about joint probabilities. So the probability of A and B, which is the probability that both it is raining and the ground is wet. So the joint probability with this notation is the probability that both A and B occur. So now let's look at how these probabilities all relate to each other. So there's some simple rules for moving from one probability to another. For example, the joint probability of A and B is equal to the product of the conditional probability of A given B times the probability of B. Or we can reverse it and say that it's equal to the conditional probability of B given A times the probability of A. Similarly, we can represent the probability of A as a marginalization, where we sum over all of the possible values that another event can take within a joint probability. So the probability of A can also be represented as the joint probability of A and B, where we simply sum over all possible values of B, getting rid of any impact that it could have. And so in this case, we call the probability of A the marginal probability. So you can call this two different things. You can say it's simply the probability of A, or you could say it's the marginal probability of A. When you add that extra word marginal, you're implying that there's some additional event that you're integrating or summing out. And similarly with B, we could say the marginal probability of B is equal to the joint probability of A and B, where we've summed or integrated over all possible values of A, where when A is discrete, it can take a finite number of values we sum. When A is continuous, the sum becomes an integral. Okay, so these three simple equations allow us to say some interesting things and even derive Bayes' rule. So for example, the first line alone is enough to say the following two lines, the first equality in the following two lines. So for example, these three terms are equal to each other. If we focus on this equality here, using simple algebra, we can say that the conditional probability of A given B is equal to the product of the conditional probability of B given A times the probability of A divided by the probability of B. And exactly the same down here, except A and B is reversed. And also, because of the representation of the probability of A and B as marginal probabilities, we can say that the probability of B is a marginal probability of the joint probability of A and B, where we've integrated or summed over A. And then the joint probability, again, up here, can be written as a conditional probability times a marginal probability. And so we have this sum in the denominator. And so simply notice that for both of these terms, the denominator is equal to the sum of the numerator over all possible values of A. And so what this is doing is it's simply normalizing the numerator so that it's a probability distribution. And so this is known as Bayes' rule. So Bayes' rule is nice because in practice it allows us to quantify what we don't know using probability distributions. And so imagine that we wanted to say something about the probability of B, given knowledge that the event A happened. So Bayes' rule says that the probability of the event B after knowing the event A, in this case we would call that the posterior probability because it's the probability after obtaining some data, A, is equal to the probability of A given B. In this case, this is the likelihood. So it's the likelihood of observing what we saw given a certain setting for B times a prior on B, so a probability of B that we have to define a priori. So this is a prior probability on the event B divided by the marginal probability of the event A. And so notice that when we think about what we do and don't know, that these manipulations that I've discussed on the previous slide, which were just simply conditional and joint and marginal probabilities, take on new meanings. So we can now use these terms of posterior, likelihood, and prior, whereas in reality, the probability of B given A is just a conditional probability, and the probability of A given B is also just a conditional probability. But the significance is different. The probability of B given A is our posterior belief of the unknown B given the observation A, whereas the probability of A given B is the likelihood of seeing what we saw given a certain setting for B. So they're both conditional probabilities, but we think of them in different ways. So we've discussed Bayes' rule in the context of discrete variables. It simplifies, or it can be extended to continuous random variables and continuous parameters in a very simple and straightforward way. So in this case, instead of probabilities, we'll talk about densities. So let's think of an example where theta is a continuous valued model parameter and x is some data that we possess. So then, using Bayes' rule, the posterior probability of the model parameter or the model variable given the data that we've observed is equal to the likelihood of the data given the model variable times the prior probability of the model variable divided by the integral of the numerator over all possible values of the model variable, which is just the marginal probability of the data. So in this case, using Bayes' rule for model learning, we possess the knowledge of everything necessary in principle. So for example, the probability of the data given the model variable, which is the likelihood, is known from the model definition. So we define this term here. We define some generative distribution on our data given some model with its unknown variables. And then the prior probability on the model variables is also something that we're going to define. So what we want is the posterior probability of all model variables, and we can write that in terms of things that we know. And then the only question that remains is whether we can calculate this integral in the denominator in order to give a closed form analytic expression for the posterior probability.